Welcome to today's Explainer. So I know you already have the basics down when it comes to set theory, and you're ready to dive into the really good stuff. You want to understand Cartesian products, relations, range and domains, arrow diagrams, directed graphs, and functions. Well, you are in exactly the right place. Think of me as your guide today. We're going to build on your foundation step by step, moving from isolated sets to seeing exactly how they connect. Let's tackle this mathematical staircase together, all right?
Here is our quick agenda for today. We're going to cover connecting sets with Cartesian products, defining mathematical relations, understanding domain and range, visualizing with arrow diagrams, visualizing with directed graphs, and finally, the strict rule of functions. Let's jump right in. Section 1, connecting sets with Cartesian products.
Okay, so before we can find a specific relationship between two sets, we really need to know every single possible way they could ever be connected. Think of the Cartesian product as the ultimate combination generator. It's a complete, exhaustive list of all possible connections between two sets, and we write it as A cross B. In this product, we're forming ordered pairs. The rule is simple. The first element always comes from the first set, set A, and the second element always comes from the second set B. This concept is actually surprisingly intuitive when we use a real-world analogy. Imagine set A contains days of the week, like Monday and Tuesday, and set B contains meals, like breakfast and dinner. The Cartesian product just pairs every single day with every possible meal without skipping a thing. So you end up with Monday breakfast, Monday dinner, Tuesday breakfast, and Tuesday dinner. You are literally just matching every single item in the first bucket with every single item in the second bucket. Pretty simple, right? But what if we don't want all of them? What if we only care about very specific pairs?
That brings us to Section 2, defining mathematical relations.
So a mathematical relation is exactly what it sounds like. It's how elements of one set are related to elements of another set. Mathematically speaking, a relation is just a subset of that Cartesian product we literally just talked about. This means we start with that massive, complete list of all possible ordered pairs, and then we apply a specific rule. We only keep the ordered pairs that actually satisfy the rule we care about. Let's look at an actual number example to make this concrete. Say set A has the numbers 1, 2, and 3. Set B has 1, 4, and 9. Now let's say our rule for this relation is the second number must be the square of the first number. If we look at all our possible combinations, only 3 pairs are actually going to fit this rule perfectly. 1 squared is 1, so we keep the pair 1, 1. 2 squared is 4, so we keep 2, 4. And 3 squared is 9, so we hold on to 3, 9. All those other possible pairs from the Cartesian product, we just ignore them because they don't follow our specific rule. Moving on to Section 3, understanding domain and range. Now that we've got our relation, we need some vocabulary to label its different parts. Don't let the jargon intimidate you. These are just helpful tags to organize our thoughts. The absolutely crucial thing here is understanding the difference between 3 terms: domain, codomain, and range. The domain is simply the set of all the first elements in your relation's ordered pairs. You can think of these as your inputs. The codomain is the entire second set that was available to you, whether you ended up using all its elements or not. But the range is only the set of those second elements that actually appear in your relation, your actual outputs. So because of that, the range is always going to be a subset of the codomain.
All right, Section 4, visualizing with arrow diagrams.
I know mathematical notation, all those brackets and commas, can start to feel a bit overwhelming. Sometimes the absolute best way to understand math is to literally just draw it out. Suppose we have 2 finite sets. To make an arrow diagram, you simply write down the elements of set A in one circle, or disjoint disk, and the elements of set B in another. Then you just draw a line, an arrow, from an element in the first disk to an element in the second disk, whenever those two are connected by your relation. It's great because it takes abstract numbers and turns them into a super clear visual map. Reading these diagrams is a total breeze once you know the secret. The start of the arrow, like where it originates, is always your domain element. The physical path that the arrow takes across the page represents the mathematical relation itself. And the destination, where the arrow finally points, is your range. You're just following the path from input to output. But hey, what happens if a set has a relation with itself? Like, what if we don't have a separate set A and set B, but just one single finite set interacting with its own elements? That takes us to Section 5, visualizing with directed graphs. When we want to map a set's relation with itself, we use what are called directed graphs. So instead of 2 separate circles, we draw the elements of our single set as points, which we call nodes or vertices. If the number 1 relates to the number 2,
We just draw an arrow pointing straight from node 1 over to node 2. We're basically mapping the internal network of a single set.
And this brilliantly illustrates just how complex these internal rules can get. You can have arrows pointing from one node to another, or, and this is a really cool part, an element can actually relate to itself. When an element relates to itself, you just draw a loop. Notice node C on the left and node 3 on the right here. The arrow starts and ends on the exact same point. It's just a fantastic way to visually organize complex internal rules. You are doing fantastic work so far, by the way. We have successfully climbed to the final, most important step of our mathematical staircase for today. Section 6, the strict rule of functions. Okay, this is where we tighten up the rules. A function is a relation, yes, but it's a relation with an incredibly strict rule. A function is a relation where each element of the domain is paired with exactly one element of the range. No exceptions. Think of it like a perfectly reliable machine. Every single time you press a specific button, your input, you absolutely must get one and only one specific result, your output. Take a look at this arrow diagram. The green circle is our domain, set A, and the blue circle is our range, set B. Notice how every single number in the green domain circle has one and exactly one arrow leaving it. The number 1 only goes to 2. The number 2 only goes to 4. There's zero confusion here. There are no two arrows coming out of the same green number. This highly strict one-to-one mapping rule originating from the domain is exactly what makes this a function. Okay, time to put your new knowledge to the test. I'm going to show you a relation, and I want you to look closely at it and tell me if it qualifies as a function. Are you ready? All right, here we have our green domain, numbers 1 through 5. But really look at the arrows. Every single number from 1 to 5 is firing an arrow directly at the number 4 in the blue range circle. Think about that strict rule we just discussed regarding the domain's input values. Is this a function? The answer is yes, it absolutely is a function. I know, it might look a little weird at first glance, but remember the golden rule. The x value, the input, can only be assigned to one y value. The number 1 only goes to 4. The number 2 only goes to 4. None of the inputs are firing two arrows at once. Sharing an output is perfectly fine. Think about it. Multiple different buttons on a machine can do the exact same thing, as long as one single button doesn't unpredictably do two different things at the same time. And that rock-solid predictability is exactly why we care so much about this. As our source material highlights, each input has one and only one output, making functions very useful in mathematics. If you put a number into an algebraic equation, you need to know exactly what is going to pop out the other side. Functions are literally the ultimate reliable tools that make higher-level math, physics, and computer science possible. You have done an incredible job today, building all the way up from basic sets to these strict mathematical functions. Before we part ways, I want to leave you with a quick thought to keep that curiosity fired up. Look around your house today, or think about the software on your phone. If functions require one distinct, predictable output for every single input, what real-world systems around you operate strictly as mathematical functions? Think about it. Until next time, keep exploring and keep learning.